All right, good morning. How's everyone doing today? I'm doing well too, thank you. Felt like a short weekend, but it was good. All right, let's start with any questions, and then we'll go on and we'll look at ODP 207, I believe it is, and then I want to talk more about linked lists. But any questions up front? All right, well, let's just jump into the ODPs then. All right. So 207. This is related to PA2. It's not exactly something you're going to do in there, but it's working with the same structures and doing the same kinds of operations. But it's a small piece of something you might do. Let's see. Oh, actually, I do have a question. How would we determine if we have run out of memory? Does malloc somehow return something specific? Yes, if you run out of memory, malloc will return null, just like getNode returned myNull. So whenever you call malloc, you should always check the value you get back, and if it's equal to null, then you're out of memory. That's not going to happen unless something has gone wrong, so I'm not going to test that when I run your program, and there's no easy way for you to test that yourself. But put it in your code anyway. It's just good practice. 206, I looked at, and it's exactly the same as 205, so I think I overwrote something. But I have no idea what I had originally had for 206. So, but this seems like a good next ODP to do anyway, because I want to do assessments on dynamic memory-based linked lists. And so this seems like a good one. With 32 gig of RAM, yeah, it's going to be hard to test. I mean, you can do it, you can run out of memory, but it's tricky to run out of memory in a way that lets you continue running code and looking at output and so on and so forth. Unless you're very aggressively chewing up memory, because, things will use memory and release memory. And if you're running something that's, very desperately grabbing everything that's available, it's probably going to crash your system. But, it's fun to try. The other option is, put a wrapper around malloc and just have it return null after 10 calls or something. That would be fun. Just don't forget to unwrap it later. All right, ODP 207. So we're working with the struct nodes that we're seeing in PA2. So 2 fields instead of 3, a data node and a next field. The next is a genuine pointer to a struct node. So it's declared like that. And your whole purpose here is to write a function named link, okay? And link does the following. It takes 2 pointers to nodes, and it makes the first one point to the second. The first node point to the second. So here's an example. Let's suppose this is our main test program. And we've defined, what a struct node is somewhere, so let's make a pair of nodes. So we'll do a struct node star first. and we'll malloc, you know, size of struct node. I'll write it in once. And then we'll do a second one. And so this creates a pair of nodes in memory. And they are completely uninitialized. Totally random values in these fields. So if I call link and I make my arguments exactly first comma second, since first is a pointer to a node and second is a pointer to a node, I'm calling, you know, exactly according to the prototype. I should be passing two addresses. I don't put ampersands in front of these because they're already declared to be addresses. They're already declared to be things pointing to something. So if I declare just a struct node named first, right, then I would use ampersand first to get its address. And I wouldn't have to do malloc, because if I make a variable of some type, the compiler and linker set up memory for that. But we'll stick to using pointers from here on out. So we'll allocate space by calling malloc for first and second. And then if I just say link first second, what that should do is take this field of this node and set it to point to the second node. This is just one line of code. It's really just first arrow next equals second. But make peace with that, right? Don't just do that because I said it or because it works or because someone said something about it, right? And how could we test this? Well, if you run your test program in GDB, it's really easy, right? If you print the value of second, it should show you the address where that's stored. If you print first, arrow next, that should have the same address after you call link. If you do this before you call link, this will be some unknown value, probably 0. And then call link, and this should change to be equal to whatever the address of second is. All right, so that's your ODP 207. One line of actual code. Put it together with your own test code. Run it in the debugger. Take a look at it. Make sure it makes sense, and then compile it with the test bed, and then assess it in the usual way. Does arrow next say the pointer to the next field of first? Yeah. Arrow next it means dereference the pointer, find the actual node that this refers to, and use the next field of it. So if first is a pointer, first arrow next gets you this block, this piece of it. First arrow data would get you that piece. And that right there is the whole trick of working with any of these structures that are built at runtime in memory. So if your brain wobbles a little around this, that's good. That's the point that needs to be worked out.
So if first is declared as a star, so pointer, Why would we still use arrow notation? Because aren't we dereferencing the pointer now to its value?
So first is a pointer, right? Because we declared it with a star. Um, if we tried to do something like first dot next, that's going to give me a compile error. Because first is not a structure. First is a pointer, right? It's a memory address. To use this dot next notation, the thing that comes before it has to be a struct node. And so how do I find a struct node? I say star first. And then this is just a shorthand, neater way of writing that. But it means that. So I read this as, first is a pointer, take the thing it points to, and give me the next field. Does that make sense?
Yes, it does.
Okay, cool. Alright, so I have a series of ODPs queued up this week. 207, 208, 209. I have a 210 that I would have to give you. I still got time for a 210, but that would be due the same day as your PA2, so it seems silly. But anyway, there's a series of assessments coming up, okay? You don't want to get these confused. Everything is already posted in /temp, so you can look at the readmes for 208 and 209. You can write your own test code for 208 and 209, but you cannot assess those. Okay, so suppose suppose you're very ambitious and you looked at the README for 208 and you've written the code for it and you've got your test program and you decide to get ahead of the curve, so you try to assess ODP 208 with build.c. Alright, anytime you run assessment, make sure you look at this, right? And don't assess your code too early. If you look at this, it says you're about to assess your code for ODP 207. And if I think that I'm assessing 208, I've got to stop. Right? If I actually go ahead and submit this for grading, it's going to overwrite my code for 207, my grade for 207. So exit out and wait until 208 is open. Yeah, I like that script you set up. That's really awesome. So yeah, somebody made a script to like help with submitting your ODPs, which is cool. On my longer to-do list, actually my really long to-do list is changing this so that you can have multiple ODPs running at once, and you can assess them whenever you like, and then I could just like post them all in the beginning of the quarter, and you could assess them at your leisure. But I haven't done that, and I suspect I never will. But anyway, okay, so we're doing 207 due tomorrow at 10 o'clock, and these ODPs are generally going to be due at 10, and the next one will open 2 minutes after that. So, and we'll talk about them in class as they open up. But for tomorrow, I'll just work on 207 and keep working on PA2, obviously. Oh, WH. Well, did you read it? So someone said they were looking around in temp, and they found wh.txt. So this was for a word index program. This is the text of Wuthering Heights. Awesome movie. So it's just I used to use War and Peace, and I've gotten tired of War and Peace. So this is Wuthering Heights, and it's nice and long. cat's even better because it goes out without you having to. There you go. It's not as bad as SL, right? How did you make those ASCII diagrams? Just by hand. ASCII art's always a interesting thing to put inside code. And yeah, you know, just make boxes with dashes and pipes and pluses for the corners, and it's a fun way when you're at a breaking point in a project and you want to you know, change gears, go ahead and throw some ASCII art around your comments. And that's fun. Yeah, it is becoming a lost art. Although I have an app on my phone that'll take a picture and turn it into ASCII art, and that's kind of fun. All right, so any questions on the ODP? Yeah, definitely. Comic Sans. All right, let's take a look at the GDB quiz on Canvas. So we started looking at some of the quizzes last week. Yeah, I like cool fonts. All right, so we started this on Friday. Let's go through this in more detail. Let me hop back on the server. So this is more of a lab than a quiz, right? So it tells you to go ahead and run the debugger on /temp/g1, start with the start command, and then do various things to answer these questions. So I can gdb/temp/g1 and say start, and now I'm running my debugger. I compiled this with source code, so you can see the source code, right? But it doesn't necessarily help you in answering these questions. But of particular interest, I have a structure defined in here called myStruct, and it's got a number of fields to it. So we want to use GDB commands to understand what's going on with this code. So question 1, again, we did this last week. Set a watch point on I, run until I is equal to 5, and then see what the value of x is. So watch points, right, you can set up just by saying watch name of variable. And if we run this, anytime that the variable changes value, we'll come back to our debug prompt. And it'll show us the old value and the new value. This happens after the variable changes. Okay, breakpoints come back to you before the line you're breaking at executes. The next command shows you the line before it executes it, but watch points show you after the variable's changed value, because it doesn't know it's about to change. So this is the new value. So just keep saying continue until I changes to a 5, and then print out the value of x. And that's your answer for question 1. Question 2, how many bytes are allocated for the structure myStruct? Use the size of, right? So if I say print size of x, that'll show me the size of x, the variable, right? But use size of with types. Print size of int, for example, or print size of float, or print size of double. Was Comic Sans really created for Microsoft Bob? That's cool, I didn't know that. I want a Clippy font. All right, so how many bytes are allocated for struct myStruct? So just print size of struct myStruct. All right, question 3, what's the starting address of the array named data? So there is an array in here named data, It's an array of structs from we'll just list again. So there's a struct, my struct data bracket 10. So remember, when you declare an array in C, the name of that array refers to the address where the array begins. So if I have integer I bracket 10, then I, the single letter variable, refers to the address where that array begins. So what I'm asking you here in question 3 is, what's the address where the array named data begins? And so play around with a print command and figure that out. This should also be the address of data bracket 0, but you can find this by printing ampersand data bracket 0. Let's see, you just got here. Cool, welcome. We're going over the February 3rd quiz. Yes, we're going over the GDB quiz. It says 1 in G1.c if you say list. You're not seeing that when you first go in and say list? Interesting. Do the same. Try saying list space 1. Like that. Can you paste into chat what you're seeing when you say list 1? All right, can you hop on to, can you stay on Zoom and screen share with me right after class so I can see what you're doing? Cool. Yeah, I have used this for a few years in a row, and it's different every year for some reason, and I rebuilt it yesterday and reposted it, and so it's very likely that, very possible that something wonky happened. Alright, so print the address of data bracket 0, that's just ampersand data bracket 0, print the address of data 1, data 9, and you should see a pattern here, right? A pattern related to the size of this structure that you discovered in question 2. But as you're doing this, what you want to be doing is making yourself like a memory map. So draw a picture of the memory of your computer. Here's our array data. Here's element 0, here's element 1, and so on down to element 9. Figure out the addresses where each of these begin. Right, figure them out by printing them in GDB, add them to a picture, and then hypothesize a formula for the address of data bracket I. Where would the ith element be located in memory? And this is what the compiler has to figure out. Because if you're going to write code that says, you know, for I equals such and such, print data bracket I, it's got to code that into assembly language code that somehow gets to the ith element in the array. Which means it has to figure out or conjure up a formula for where each element begins. So that's what you're doing in that question. So we're doing the job of the compiler, exactly. All right, so and it's one of these formulas that'll work for data bracket I. Now you want to start digging into the structure itself. All right, GDB should work. All right, so let's dig into the structure itself. So the structure contains a number of fields. Well, I just gave you source code for it, so we can just look at the source code. So yay, success, cool. So there's a number of fields in here, right? We want to explore how those are stored in memory inside the struct, because we already know from looking at our structures in PA1 that there's sometimes space in between the different fields of a structure. So so your goal here is figure out how this structure is organized, what's stored first, what's stored second, and so on. So how does this work? Pick one element of your data array, like data bracket 0, and print its address. Figure out where that structure begins. And now if you want to know about, the field called F1, what can you do? You can say print the address of data bracket 0 dot F1. And that gives you, some number where F1 is stored. And then if you print the address of data bracket 0 dot X, that'll give you a different address, and maybe that's stored right here. So break apart what's going on with this structure in memory by printing the location of different fields in one particular element of data. Alright, so print the address of different fields to figure this out. And when you're done, you should be able to tell me which field is stored first. Alright, so that's the answer for question 8. Question 9, use the size of function to calculate the size of each field. So we know, x is an integer, c1 and c2 are characters, and so on. If you print size of int, size of car, size of double, add those up, tell me how many bytes we need to store that information. If we were to pack everything in as tightly as possible, how many bytes do we need? That's your answer for question 9. Question 10, you'll find the total number of amount of space you need is less than 32, which is the actual size of the structure, which means that somewhere in this memory map there are gaps. Could be one gap, could be multiple gaps. So figure out the address where the first unused byte is. That's your answer for question 10. All right, does that make sense what you're trying to do? Yeah, I forgot that even when you compile with debugging symbols, you still need the source code file to be accessible. Does this quiz give instant correct answers for fill in the blanks? I don't know. I don't really understand Canvas quizzes very well. Let's see what I set up. Shuffle answers, allow multiple attempts, keep the highest, unlimited attempts, let students see the quiz responses. Incorrect questions will be marked in student feedback. So it does not show the correct answer, but it does give you some feedback. Yeah, you can take it an infinite number of times. All right, let's see. So quiz 2 is due on January 29th, and I think we already looked at this one on Friday. So this is just some questions about structures and about using the arrow notation. And then the question about what causes a seg fault. So we talked about that one already. Quiz 3 is the other one that's coming up, and this is due on February 3rd, same day as the GDB quiz. Nope, just GDB/temp/G1. Right, just do exactly as it's described up here. Oh no, we're going 215 now. Alright, so quiz 3 is a linked list quiz, and I think you've already got more than enough experience and knowledge of linked lists to answer these questions. So, which of the following is true about memory in linked lists? A sentinel node in a linked list is abstract data types, and then I don't remember what this question was. Linked lists compared to arrays. So work on those quizzes. Let me know if you have any questions. Let me give you a disclaimer though. The GDB quiz is long. If you've never done this, if you haven't played around with making memory maps, it's going to take some work. Okay? These other quizzes you can probably bang through in 5 minutes and get a pretty good score, because they're just, you know, short answer, multiple choice, things like that. The GDB quiz will take some work. You have to actually get onto the server, you have to go into GDB, and you have to explore and think and analyze. So so don't start that 5 minutes before it's due. But it's an important quiz. It's good practice for things that you want to be able to do as you develop your code for PA2 and for other projects. Let's see, temp G1 still doesn't work for me on list command, but when I cd temp and run it, it works fine. Alright, that should fix it. Yeah, recompile 3 times. Alright, any other questions on the quizzes or any lingering issues on G1? Always 3 times. Alright, I want to talk about some variations on linked lists, and this will probably do it for this subject. And we're going to go on, probably tomorrow, we're going to start talking about stacks and queues, which are our next data structures to work with, and maybe the next programming assignment. I haven't decided what PA3 will be yet. But stacks and queues can be implemented, among other things, with linked lists. So we'll start talking about those probably tomorrow. But let me talk a little bit more about other types of linked lists. And we've got, our traditional linked list, which looks like this. So there's a data field and there's a next field. Well, one thing we'll do sometimes is we'll add a new field so that each node also points backwards to the prior node. Right, and this is a doubly linked list. So we can follow our nodes forward, as we've been doing, but when we get to a particular node, we can also go backwards. And why would we possibly want to do that? What could be an advantage of having these back pointers? Reverse sort, yeah. Start in any position, yeah. If you need to go back to something you aren't keeping track of, you don't have to start from the beginning again. So there's a lot of advantages, right? If we're building our list in some sort of sorted order, we can get a reverse sorted list by moving backwards. We can modulate around some point, because we don't just have to move forward, and we can go back to a prior node without having to start from the beginning or keep track of what the prior node was. So why would we want to modulate around something? There's a characteristic of data access, which is spatial locality. There's times when you're searching, say, a set of data, and because of the nature of the search, if you pull a piece of data from this location, there's a good chance that the next thing you're going to want to pull is somewhere near that, in terms of if it's a linked list, a small number of nodes from there. For example, and you wouldn't do this, suppose you had a linked list of real estate listings, right? And they're sorted by zip code. Well, chances are, if I'm pulling up a real estate listing for 98663, the next one I pull up is probably going to have the same zip code or something close to it, right? Unless I'm a realtor or something, I'm probably not pulling up zip codes from all over the country, right? So there's locality of data, and a lot of times we take advantage of that when we organize information in a database or whatever. So if we were doing that kind of access in a linked list, right, we might get over here to one entry, and it might be the next entry we want is just 2 spots before it. Well, with a regular linked list, you've always got to start at the beginning and move forward. With a doubly linked list, we could start where we are. We could see that the value we're looking for comes somewhere before this, and we could just start moving backwards. For coding, yeah, the big advantage is we don't have to do this pair of pointers anymore, this previous current thing that we had to do every time we wanted to add or delete. We needed to know the prior node so that when we got to the node where the action was happening, we had something that referred to this node here so we could adjust its pointers. So what does that look like? And yeah, I am using a dip pen. That was a present from my fiance, and I like dip pens, so it's fun. It slows me down. So let's look at a doubly linked list node. So there's a data field, there's a next field, and there's a previous field. So a little more memory. Yeah, so exactly, trade-off. A little more memory for a little more versatility. And you know, if our integer is you know, if our data field is an integer, this is, you know, an extra 50% of memory. But if our data field was something bigger, this might be, you know, an incremental bump in the size of the node. So what will this look like? Let's say we have a set of nodes like this. And let's say here's a 10 and a 20 and a 30 and a 40. And let me do these in pencil. I'm not going to make my previous pointers point up here to the top, because that just gets spaghetti ballish. But you know, it's the address of the node, so this is technically pointing to the address where that data field begins, but I'm going to simplify my drawing a little. So let's suppose we want to delete the 30 node. So start from the sentinel. Let's see. I think it's more common to find doubly linked lists than single. We don't really worry about memory that much. Linked lists aren't really used for storing terabytes of data, so we don't usually worry about how much space they're taking. And it's just so much more convenient to be able to move back and forth. But I don't know. That's just my feeling. So let's say we want to delete the 30. So, you know, again, we have some sort of current node. And we check to see if current data is the number we're deleting. Well, it's not. So what do? We set current equal to current next. So we move down and we make current here. And current data is 20. That's not what we want to delete. So we set current equal to current next. And now our current node is right here, and current arrow data does match the number we want to delete. Alright, so how do we do this? Well, the first thing we need to do is change the previous node's next to point where? To current next. Well, the previous node is C arrow previous. That's this node. And we want its next field to be equal to whatever the current node is pointing to. That's C next. So here's the current node. And let me label these. So current node, the thing that it points to is this block. The previous field is this block, which is a pointer to this node. This arrow says take the thing it points to, which is this node. This says take the next field. So now this left-hand side refers to this box right here. And we're setting it equal to what? C arrow next. C points to this block. The next field is this, which is a pointer to here. So that changes this block to point to the 40. And so we've got that hopping over the node we're deleting. And this is where this arrow notation will start to work for you, right? I'll read this as C, go back to the previous, take its next field, set it equal to C next. So take a shot at putting something in chat. What's the other line that I need to set this arrow to point back to, in this case, the 20 node. So someone said C arrow next arrow previous equals C previous. And that's exactly right. Right? I don't have a previous variable. I only have one variable, which is just C. Right? If I'm doing a pair of pointers, then I have a variable pointing to that previous node. I don't, but I can get to the previous node through my current node. So the next node, C arrow next, is this 40, and I want to change its previous value to be whatever C's previous value is. And that's going to come over here. This is C arrow next previous. Set it up to whatever C previous is. So that's a powerhouse pair of statements right there, right? When you grok this, when you make peace with this, and it feels natural, right? You've arrived. There's like an aura around you when you go out at night and stuff like that. This is really describing. So to me, right, having suffered through the learning process, this to me means this. Right? This C arrow next arrow previous says C arrow next arrow previous. Right? And your brain will connect the idea of following these arrows with following these arrows. However you draw these pictures, and whether they're on paper or in your head. Alright, and then we need to free C. So someone asked about a garbage collector. And on systems like Java, if I did this, there would be nothing referring to C anymore, right? I have a sentinel node referring to some node back here. I had a variable C that was referring to this. Once I change the value of C, so C is, some other node in some other piece of code, there's nothing referring to this anymore. There used to be an arrow here, well, that's pointing somewhere else. There used to be an arrow here, that's pointing somewhere else. This is a lost node. Right? This is what Valgrind would report as a lost node. So in Java, for example, there's a garbage collector running in the background that goes around and looks for lost nodes. And if it finds one, it says, oh, nobody's using this thing anymore, and it returns it to the free memory pool. So for us, we have to free that explicitly before we change the value of C. So we would just free C. And that returns it to the memory pool. And that's your deletion. So a little more work, perhaps, but not really. It's mainly just a little bit of memory expense. But it's something we've got to keep track of, right, when we're writing our code. And then insert is the same thing. If you're putting a node in between, when you get to the spot that you want to insert the node before, well, C arrow previous arrow next equals new node. C arrow C previous equals new node, and then new node arrow previous equals C previous, and new node next equals C. Something like that. Play around with it. We're not going to do this for PA2, right? PA2 is a singly linked list. But it's it's an option. All right, so we can talk about circular lists. And a circular list, basically the last node points back to the first node. And it simplifies some coding because you don't have to worry about, my last node points to null and that's a special value, so now I need to go back to the beginning of the list. Basically just makes a big loop. But you've got to be aware of that. For example, when you try to print out the contents of your list, If you don't know that you're looping back, you're going to print forever. And there's a good chance you'll accidentally create a circular list in PA2 by doing something not quite right in your delete function typically. But sometimes we deliberately make circular lists. Alright, we are out of time, so I will leave it there. And we'll start talking about stacks and queues tomorrow. And that'll be a change of gears for us for a while. Work on the ODPs, keep going on PA2, bring questions, and I will see you next time.